This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. We're diving into a fascinating world of HTTP headers, specifically the response headers from a recent server interaction. It's a seemingly simple set of data, but it reveals a lot about security, caching, and how websites operate.
Indeed. The HTTP response headers provide a crucial layer of information, controlling how browsers and other clients interact with the server's response. They're essential for a smooth and secure web experience.
Let's start with the status code, 200 OK. What does that tell us?
A 200 OK status code simply means the request was successful. The server received, processed, and understood the request, and is now sending back the requested resource. It's the most common and positive response you'll see.
Right. But there's much more than just the status code. We see headers like content type, cache control, and several security-related headers. Let's unpack those. The content type header specifies the type of content being returned. In this case, it's text/HTML, charset OTF8. What's the significance of the charset?
The charset OTF8 part is crucial. It indicates that the HTML content is encoded using UTF-8, a widely used character encoding that supports a vast range of characters from different languages. This ensures that the web page displays correctly regardless of the user's language or location.
Next, we have several headers related to caching, cache control, pragma, and expires. Why are these important?
These headers instruct the browser and intermediate caches, like CDNs, on how to handle caching of the response. Cache control, no cache, no store, max age 0, must revalidate, and pragma, no cache, explicitly prevent caching. The expires header further reinforces this by setting an expiration date far in the past. This is often used for dynamic content that changes frequently.
The response includes a number of security headers. Let's discuss content security policy, referrer policy, X content type options, X frame options, and X XSS protection.
These headers are critical for mitigating various web vulnerabilities. Content security policy defines a whitelist of sources from which the browser is allowed to load resources, preventing attacks like cross-site scripting. Referrer policy controls what information is sent in the referrer header, protecting user privacy. X content type options, NOSNIF, prevents the browser from guessing the MIME type, thwarting MIME sniffing attacks. X frame options, same origin, prevents clickjacking by restricting embedding the page in an iframe from other origins. Finally, XXSS protection enables the browser's built-in XSS filter.
We also see a set cookie header. What's the significance of the HTTP only flag?
The HTTP only flag is a crucial security measure. It prevents client-side scripts, like JavaScript, from accessing the cookie, making it more resistant to cross-site scripting attacks. This significantly enhances the security of the session cookie.
Let's briefly touch upon Vary, XRobots tag, content encoding, P3P, Alt SBC, and transfer encoding.
Vary indicates which request headers the response depends on, influencing caching behavior. XRobots tag provides instructions to search engine crawlers, in this case preventing indexing. Content encoding zip shows the response is compressed using zip, reducing bandwidth usage. P3P is an older privacy header, largely superseded by other mechanisms. Alt FTC advertises alternative services like HTTP/3. Finally, transfer encoding chunked indicates that the response body is sent in chunks.
The server header identifies the web server software, and the date header indicates the time the response was generated. Why are these included?
The server header is mostly for informational purposes, though it can sometimes be exploited in attacks. The date header is important for caching and debugging purposes.
Considering all these headers, what can we say about the overall security posture of this server response?
The server demonstrates a strong commitment to security. The inclusion of multiple security headers along with the HTTP-only flag on the cookie indicates a proactive approach to mitigating common web vulnerabilities.
So, a seemingly simple HTTP response header actually reveals a wealth of information about the server's configuration, security practices, and how it manages content delivery.
Precisely. Understanding these headers is crucial for both developers and security professionals.
That was a great discussion. Thank you for your insight. This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today we're diving into a fascinating paper exploring a novel approach to scaling language models, focusing on scaling up test time compute with latent reasoning, a recurrent depth approach. It challenges conventional wisdom about how we enhance these models.
Exactly. The paper proposes a radical shift from scaling model size or relying on extensive chain of thought prompting to improve reasoning capabilities.
Instead of adding more parameters or training data, they're focusing on increasing computational power at test time. How does that work?
It leverages recurrent depth. The model iteratively processes information within its latent space, effectively thinking more deeply without generating additional tokens.
So it's like giving the model more time to ponder a problem rather than giving it more information up front? Let's unpack this concept of recurrent depths. Can you explain how it differs from traditional approaches like chain of thought prompting?
Chain of thought methods require training data that explicitly demonstrates step-by-step reasoning. This approach, however, allows the model to reason implicitly within its continuous latent space, bypassing the need for such explicit training. It's a more natural way to mimic human thought processes.
That's intriguing. So the model is essentially performing internal computations without needing to verbalize each step?
Precisely. The recurrent unit iteratively refines its internal representation, leading to improved performance without the constraints of a limited context window or the need for specialized training data.
The paper mentions scaling a model to 3.5 billion parameters and training it on 800 billion tokens. What were the key aspects of their training setup?
They employed a scalable recurrent architecture, detailing both macroscopic and microscopic design choices. The training involved techniques like truncated backpropagation to manage the computational demands of the recurrent depth. They also paid close attention to optimization strategies and learning rate scheduling.
And the hardware? Training models of this scale requires significant resources.
Absolutely. The paper describes the compute setup, including details on device speed, parallelization strategies, and interconnect handling. They meticulously documented their training timeline to provide transparency and reproducibility.
What kind of results did they achieve? Did this recurrent depth approach actually improve performance?
Yes, significantly. They evaluated the model on standard benchmarks as well as more challenging math and coding tasks. The results showed substantial improvements, sometimes dramatically so, effectively reaching a computational load equivalent to a 50 billion parameter model.
That's a remarkable increase in effective capacity. Were there any particular tasks where this approach excelled?
The paper highlights that tasks requiring more complex reasoning benefited most from the increased computational load at test time. Tasks requiring less reasoning converged more quickly. This suggests that the recurrent depth allows the model to effectively utilize more compute for more challenging problems.
The paper also suggests that this recurrent depth approach simplifies LLMs in several ways. Can you elaborate?
Yes, the recurrent depth enables zero-shot adaptive compute at test time, zero-shot KV cache sharing, zero-shot continuous chain of thought reasoning, and zero-shot self-speculative decoding. These are all significant advantages over traditional methods.
These zero-shot capabilities are impressive. What underlying mechanisms seem to emerge at scale in these recurrent depth models?
One key observation is path independence. The model's ability to reach a solution seems less dependent on the specific sequence of computations, suggesting a more robust and generalizable reasoning process.
How does this work compare to existing research in the field?
The paper provides a comprehensive overview of related work, highlighting the novelty of its approach and its advantages over existing methods. It positions this recurrent depth approach as a significant advancement in the field.
And what are the next steps? What future research directions are suggested?
The authors outline several promising avenues for future research, including further exploration of the emergent mechanisms, investigation of different recurrent architectures, and scaling to even larger models and datasets.
This research seems to offer a compelling alternative to traditional methods of scaling language models. What are the broader implications of this work?
It suggests a paradigm shift in how we think about scaling language models. Instead of solely focusing on increasing model size or data, we can explore ways to enhance computational power at test time, leading to more efficient and powerful models. This could have significant implications for various applications requiring complex reasoning.
It certainly opens up exciting possibilities. The focus on latent space reasoning and the potential for zero-shot capabilities are particularly noteworthy. Thank you for this insightful discussion.
You're welcome.
This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today we're diving into a fascinating paper titled Simple Test Time Scaling. It challenges the conventional wisdom around large language model, LLM development, suggesting a surprisingly simple approach to achieving strong reasoning performance.
Indeed. The paper proposes that significant improvements in reasoning capabilities can be achieved not through massive increases in training data or model size, but through clever test time techniques.
That's a bold claim. So what's the core idea behind this simple approach?
The key is a two-pronged strategy. First, curating a surprisingly small, high-quality dataset, and second, enjoying a novel test time technique called budget forcing.
A small dataset? That seems counterintuitive given a trend towards ever larger models and datasets. Let's talk about this dataset. The paper mentions a dataset called S1K consisting of only 1,000 questions. How did they manage to achieve such good results with such a small dataset?
The secret lies in the careful curation of those 1,000 questions. They weren't randomly selected. Instead, the researchers prioritized three key criteria: difficulty, diversity, and quality. They started with a much larger pool of 59,000 questions, meticulously filtering them based on these criteria.
So they weren't just grabbing random questions from the internet?
Absolutely not. They drew from a variety of sources, including established benchmarks like Math 500 and AIM, but also created new datasets focusing on probability problems and quantitative reasoning puzzles. The goal was to ensure a diverse range of challenging problems.
And the quality aspect, how do they ensure high quality?
They used the Google Gemini Flash Thinking API to generate reasoning choices and solutions for each question. This provided a consistent, high-quality standard. They also manually inspected samples and removed those with formatting issues or other problems.
Now let's move on to the other half of their approach, budget forcing. Can you explain how this works?
Budget forcing is a test time technique that controls the amount of computation the model uses. It works by either forcefully terminating the model's thinking process if it exceeds a predefined token limit, or by encouraging it to continue thinking if it stops prematurely.
So it's like setting a budget for the model's thinking time.
Precisely. If the model tries to stop too early, the system appends a wait token, prompting it to reconsider its answer. This iterative process often leads to the model correcting its own mistakes.
That's a clever way to improve accuracy without retraining the model. It's almost like giving the model a chance to double-check its work. The paper compares their model, S132B, to other state-of-the-art models, including OpenAI's O1. How did S132B perform?
S132B, despite being trained on a significantly smaller dataset, achieved competitive results, exceeding OpenAI's O1 preview on certain benchmarks by up to 27%. It also demonstrated a clear test time-scaling behavior, meaning its performance improved with increased computational budget at test time.
That's remarkable. It suggests that the quality of the data is more important than sheer quantity.
Exactly. The paper's ablation studies strongly support this. Simply increasing the training data size to 59,000 examples didn't yield a significant improvement over the carefully curated 1,000 examples in S1K.
The paper also includes ablation studies. What did those reveal about the importance of the three criteria used for dataset selection?
The ablation studies highlighted the crucial role of combining difficulty, diversity, and quality. Using only one of these criteria resulted in significantly worse performance. For example, selecting only the longest reasoning traces improved performance on one benchmark, but hurt performance on others.
The paper also compares different test time scaling methods. What were the key findings there?
The researchers categorized methods into sequential and parallel approaches. They found that their budget forcing method, a sequential approach, offered the best controllability and scaling behavior, leading to the strongest performance. Other methods, like rejection sampling, surprisingly showed an inverse scaling trend.
Why do you think reaction sampling performed so poorly?
The authors hypothesized that shorter generations, often selected by rejection sampling, tend to be correct because the model was on the right track from the beginning. Longer generations, however, often indicate the model made mistakes and was backtracking, leading to incorrect answers.
The paper emphasizes the sample efficiency of their approach. What makes it so sample efficient?
The authors suggest that the pre-training of the base model already provides a foundation for reasoning. Their fine-tuning on S1K essentially activates and refines this existing capability. This is similar to the superficial alignment hypothesis observed in other research.
So it's not about teaching the model to reason from scratch, but rather about fine-tuning its existing abilities?
Precisely. And the budget forcing technique further enhances this efficiency by allowing for test time optimization without requiring additional training data. The paper concludes by suggesting several avenues for future research, including exploring the combination of budget forcing with reinforcement learning.
The paper also briefly touches upon parallel scaling methods such as majority voting and REBASE. How do these compare to the sequential approach?
Parallel methods offer a way to overcome the limitations of sequential scaling, particularly the context window limitations of LLMs. While majority voting provides a simple way to aggregate multiple independent runs, REBASE, a tree search method, offers more sophisticated exploration and exploitation, leading to better scaling behavior.
So a hybrid approach combining sequential and parallel methods might be the most effective way to further improve performance?
That's a promising area for future research. The paper's proposed metrics, control, scaling, and performance provide a valuable framework for evaluating and comparing these different approaches.
The paper concludes with an impact statement and acknowledgments. What are the key takeaways from these sections?
The impact statement emphasizes the importance of open source research in advancing LLM reasoning capabilities. The acknowledgments highlight the collaborative nature of the work and the contributions of various individuals and institutions.
The paper also discusses related work. What are some of the key trends and challenges in the field of LLM reasoning?
The field is rapidly evolving, with concurrent efforts focusing on reinforcement learning, supervised fine-tuning, and prompting techniques to improve reasoning abilities. Challenges include developing more robust benchmarks, addressing issues of bias and fairness, and finding ways to scale test time computation effectively.
What are some of the limitations of the test time scaling approach presented in the paper?
While budget forcing allows for some extrapolation of test time compute, it eventually plateaus due to inherent limitations in the model's architecture and the context window size. Further scaling will require more innovative approaches.
Are there any potential improvements to the budget forcing technique itself?
Absolutely. The authors suggest exploring variations such as using different prompting strings, incorporating frequency penalties, or adjusting temperature to avoid repetitive loops. Combining budget forcing with reinforcement learning is another promising avenue.
So, in summary, this paper presents a compelling case for a simpler approach to LLM reasoning, emphasizing the importance of data quality over quantity and introducing a novel test time scaling technique. It opens up exciting new avenues for research and development in the field.
Precisely. The simplicity and effectiveness of their approach are noteworthy, and the open source nature of their work is commendable. It's a significant contribution to the field.
That was a great discussion. Thank you for your insight.